Okay, so we're going to talk about just basic probability rules. And then the one thing that's probably going to be relatively new is kind of a formal thing called a probability model that I'll show you how to create. So let's do that. All right, generally what's in the green boxes is going to be pretty important to write down. So for us, we're going to talk about a sample space. So a sample space for a chance process is just the set of all possible outcomes. All right. So kind of while you're writing this, I'll give you an example. So let's say the chance process is to flip a fair coin once. Very, very basic chance process. We would say that the sample space is just heads or tails. Those are all the possible outcomes. All right, and so a probability model, generally, when we have something like this that has discrete, equally likely outcomes, the sample space will be a table that'll have two rows. And the first row will describe the sample space, and the second row will describe the probability for each outcome. So if I wanted to create a probability model for the chance process that I just described, I would do this. In this case, there's only two outcomes, right? Heads and tails. The probability of each outcome, it's a fair coin, is the same. They're both 0.5. And so one thing that you'll notice, you have a valid probability model if your probability should add up to 1, right? So that means that you've covered all possible outcomes. All right. So let's look at a more complex sample space. You don't have to write this down. Again, it's being recorded, so if you need to come back to this example, you'll be able to. But there's lots of games that involve rolling 2 die. And so that's our chance process here. And if I want to look at the sample space, I need to look at all possible outcomes. So one way to make this easier, because people sometimes get confused, is rolling a 3 and a 2 the same as rolling a 2 and a 3. No, those are two different outcomes. And so one way to make that more obvious is if we think of the 2 dice as being different colors. So an orange 3 and a blue 2 is different than a blue 3 and an orange 2, if that makes sense. Those are two different outcomes, right? And so when you roll 2 fair dice, 6-sided normal dice, the sample space has 36 possible outcomes. And we'll talk about this, I think we define it later, but something you've probably come across just in your math education so far is something called the multiplication principle. If you want to see how many different outcomes are possible in a chance process, that's sequential. So we can consider this sequential because rolling 2 dice is the same ostensibly as rolling 1 dice and then rolling another one right after, right? So think of it as sequential. And the way you can figure out how many total outcomes there will be is you take the number of outcomes for the first process. So rolling the first dice, there are 6 possible outcomes, right? And then you multiply that by the number of possible outcomes for each process that comes next in the sequence. So in this case, there's only 2 processes. I'm rolling 1 dice and then another dice, and each of them has 6 possible outcomes. 6 times 6 is 36, which means there's going to be 36 possible outcomes, okay? And you can see the sample space here. All right. Something that's important to differentiate from the sample space is an event. So write down what's in green. An event is any collection of outcomes from some chance process, meaning it's a subset of the sample space. And events are usually designated by capital letters, A, B, and C, and so on. So an event in the dice rolling example, they give you here, let's define event A as the sum of 5. And so there are 4 outcomes that result in a sum of 5. And so if I use probability of notation, I can say that the probability of event A occurring is just 4 out of 36. Reduces to 1 out of 9 if you like. And then I have event B, I define as the sum is not 5. We're going to find out that that's called the complement. Meaning that B equals A complement. So the complement is like the inverse almost, right? So B is not, sum is not 5, so that would be everything else, right? And we're going to define this later. Don't feel like you need to memorize these notations or anything. I'm going to give that to you formally. I'm just kind of trying to prime you for it. And so a quick way to find the complement, if we already know the probability of event A, then event B must be 1 minus that, right? Because it's everything else. So it's 32 out of 36. All right. Do you guys know the game Craps? That's the one that's depicted. If anybody goes, well, there's 2 games you'll see in movies that involve casinos, right? There's roulette, the one with the marble and the wheel, and then there's craps, and that's the one where everybody's standing around a big table that looks like a miniature pool, and they're throwing dice at the wall. Go ahead, Riley.
Is that like when you say something's a crapshoot? Like
Yeah, exactly. So shooting craps means like throwing the dice. And you're playing even if you're not the one rolling the dice, because you're making a bet on that person and what they'll roll. And it basically, I think we do a couple examples of it. There are so many bets in it, and that's why people like it so much, because you can make so many different bets. But on the first roll, you're trying to roll a 7 or an 11. And so that would be the event or the events of interest in that case. But we'll do some of those. I've never played craps in real life. It seems very intimidating because there's a whole bunch of people around the table, and there's a lot of etiquette in like table betting in Las Vegas, so it's very scary. But I've played roulette. That one's easy to play. We'll talk about that more. I'll talk about a dumb bet that I made when me and Kenton went to a to a math conference in Las Vegas a couple years back, and we were on this unit in statistics, and we had just covered some of these probabilities from roulette. So I said I'd place one bet to show them that it was like a dumb thing to do, and then I hit on it, and I made like $120 off of a $5 bet, which was like super unlikely and not the point I was trying to make. All right, here we go. Moving forward. Okay, let's try this example. Imagine flipping a fair coin 3 times. Describe the probability model for this chance process and use it to find the probability of getting at least one head in 3 flips. All right, so let's talk about the sample space first. So the thing we're doing is flipping a fair coin 3 times, right? So I'm gonna just come up with a little bit of notation here. So I'm gonna say, right, intuitively, H equals heads, T equals tails. And then let's look at our sample space. And I think this one's easiest to do vertically. So I'm just going to list it under this, right? So I flip a fair coin 3 times in the chat, or if you want to unmute yourself, if you're feeling brave. Give me one possible outcome using my notation. I flip a coin 3 times. What's one thing that could happen?
Heads, tails, tails.
Exactly. And that's all we're looking for. So that's one outcome in our sample space, right? Heads, tails, tails. Now, just because something like this, I think it's easier to go in an order where it's easy to keep track of. I'm going to do it this way. I'm going to go with the most extreme outcome first, and I'm going to say heads, 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 right? So that's the first one. And again, think of these coins as being 3 different colors. So that heads, heads, tails is going to be different than heads, tails, heads, which will be a different outcome from tails, heads, heads. Does that make sense? But now I've covered all possibilities where there's exactly one tail, right? Because I've just kind of shifted it through from last place to the middle to the first. All right, so then the next thing we do, okay, there could be 2 tails, like Katie said, right? So let's do heads, tails, tails. And this will kind of work the same way because now there's just one head. So we just have to make sure the heads, we account for it could be in any one of the 3 coins, right? So now tails, heads, tails, or tails, tails, heads. And then what's the last one?
Tails, tails, tails.
TTT, that's it. And so if you kind of come up with some organizational method like that, it's much easier to make sure you've accounted for all the possible outcomes. So there are 8 possible outcomes here, right? We can verify that with our multiplication principle. You can think of this as a sequence of 3 chance processes, right? How many outcomes for each one of these chance processes? So each one is just a coin flip, right? So how many outcomes for a coin flip are possible? Am I asking this in a weird way? You flip a coin. Yeah, okay, that's what I'm looking for too, right? And so if I use that multiplication principle that I was talking about, it's a sequence of 3 chance processes. I flip a coin, I flip a coin, I flip a coin. So if I use that multiplication principle, each one has 2 possible outcomes, so it makes sense there should be 8 possible outcomes, right? Sorry, I think I was not being super clear. All right. And the point I was just trying to make is that makes sense. That's one way you can verify that you've covered everything in your sample space. All right, so now they want us to find an event. Let's call it A. And I'm going to call A getting at least one head, right? So I want to find the probability of A. And so what I want to look at is there are 8 total outcomes. So I'm going to put my probability is going to be out of 8. And all I need to do is count up how many of these have at least one head. So in the chat, how many of my outcomes have at least one head? 7, right? Basically all but one, all of these. Great, so my probability of event A is 7 out of 8. All right. So here are basic rules. Some of these you probably know. Feel free to abbreviate. For example, the first bullet point, you could abbreviate probability is understood to be P. Has to be between 0 and 1. Probability is always a number between 0 and 1. All possible outcomes together must have probabilities whose sum is exactly 1. So that just ensures that you have a reasonable probability model. If all outcomes in the sample space are equally likely, the probability that event A occurs can be found using this formula. And that's just the normal theoretical probability formula that we'll use for equally likely outcomes, right? The one we just used in that last example. So you take the number of outcomes corresponding to event A, and you divide by the total number of outcomes. The probability that an event does not occur, we call that the complement. Is 1 minus the probability that the event does occur. The complement of an event, the notation you can use is the original event with a superscript of C. So A complement equals 1 minus, or I should say that's bad notation, I'm sorry. I should say this. The probability of A complement equals 1 minus the probability of A. All right, and last on this page, two events, A and B, are called mutually exclusive or disjoint if they have no outcomes in common and so can never occur together. That means the probability of A and B is 0. So they cannot occur at the same time. So an example of that would be like the probability of heads and tails, right? You can't flip a coin and get both heads and tails at the same time. So they are disjoint events. Okay, so these are all the same thing, just in shorthand notation, right? So that's the notation I just gave you for saying a probability has to be in between 0 and 1. Sample space has to sum to a probability of 1. Here's how you find the probability of an event in the case of equally likely outcomes. Here's the complement rule. The only thing additional that you really need to write down is the addition rule for mutually exclusive events. So if A and B are mutually exclusive, meaning they cannot occur at the same time, then the way you can find the sum of their probabilities, so the probability that either event A or event B occurs, is just the sum of the individual events. And so that's pretty clear with my simple, right? So let's call A a coin toss, then our sample space, then S is just heads comma tails. We just discussed that those are two mutually exclusive outcomes. They cannot occur at the same time. So if I would want to know the probability of, of heads or tails, then I'm allowed to just do the probability of heads plus the probability of tails, which is going to be 0.5 plus 0.5, which is 1. Which makes sense that it should be 1 because that satisfies that second bullet, because heads and tails, that's my complete sample space. So I would expect that the sum of those probabilities should add up to 1 in that case, right? Okay, go ahead and give me a green check when you're good with that. I think we got one more quick example that's not, as trivial as the one that I just did at the bottom of the screen there. And then we'll be done with this. Here we go. Randomly select a student who took the 2010 AP Statistics exam and record the student's score. And here is the probability model. So you can score a 1, 2, 3, 4, or a 5. So you might want to have a calculator handy for this one. All right. So A, if we want to show that this is a legitimate probability model, basically what we want to show is that the probability of, every outcome, which is a 1, a 2, a 3, a 4, and a 5, which is going to be 0.233 plus 0.183 plus 0.235 plus 0.224 plus 0.125. Those should add up to what value?
1.
That's it, right? And spoiler alert, you can verify in your calculator, these do add up to 1. So it checks out. This is a legitimate probability model, right? All right, find the probability that a chosen student scored a 3 or better. So I'm going to create a little notation here. I'm just going to say let x equal a randomly selected student. And then I'm going to use probability notation. And so for B, what they're asking for is the probability then that x is greater than or equal to 3, which is what's widely accepted as passing the AP statistics exam, right? And so for that, I just need to look at these 3 outcomes and their respective probabilities. So that's just 0.235 plus 0.224 plus 0.125. And we get 0.584. All right, so the probability that, find the probability that the chosen student did not get a 1. Well, we can kind of translate to that probability that x is greater than 1, right? Well, in that case, it's probably easier. There are 2 ways we could do that. I mean, in a probability model that has this few outcomes, they're both relatively straightforward, right? So greater than 1 is just these 4 probabilities. added together. And again, it's important to understand these are mutually exclusive outcomes. None of these can occur at the same time, which is why it's okay to add their individual probabilities. You can't get a 2 and a 3. You get one or the other. But just for the sake of using the complement rule, it's maybe easier to just recognize, oh, well, there's only one outcome that is a 1. So this is equal to 1 minus the probability that x does get a 1, right? So if I just do 1 minus 0.233, that's the same as adding up. That's going to leave us with the sum of those other 4 probabilities. So in this case, either way is probably equally straightforward. But if you get used to the idea of using that complement rule, when we get down the road a little bit, there will be much more difficult problems where we have, say, 100 different outcomes. And it's much easier to use the complement rule than add up like 99 probabilities, if that makes sense. All right, so what's 1 minus 0.233? That's 0.767. Okay, and that's it for our first section of the new year.